All right, and we've arrived at capacitors and capacitance. So next lecture, we will see what role potential plays in electric circuits more fully. But before we end this lecture, I want to introduce a device that I've been alluding to this whole time that's commonly found in electrical circuits of all kinds, and we have all the tools to understand it, and that is the capacitor. So that's spelled capacitor. A capacitor is a device that offers a store of potential energy, electrical potential energy. So in the same way that like a spring would store elastic potential energy. If you compress a spring, you have stored elastic potential energy in that spring, because if you were to release it, that elastic potential energy would be able to do work on some body, and therefore the elastic potential energy would be converted to kinetic energy in that thing that it did work on. And that comes in the form of the spring relaxing back to its natural state, right? So, similarly, if you charge a capacitor, you have stored electric potential energy in the capacitor, and that can later be converted into current in a circuit. So, what is a capacitor and how do you charge one? Well, it's a lot simpler than you might imagine. A capacitor is just two conductors, right? Materials that conduct electricity, separated by some insulator, and that can even be air. The simplest form of capacitor to study is the parallel plate capacitor. So we have, let's see, is there something? Yeah, let's do this one. We'll do red. And, all right. So here's one plate with its positive charge Q, and, area A. And then here's another plate. I'll do down here. With its negative charge, negative Q. And there's some difference, some separation here, which perhaps I can draw like this. Some separation D. And of course, there's some potential difference, right? So there's some potential difference, I'll say this is plate A, and this is plate B, and this is plate A. And so therefore the potential difference, VAB, exists between the two plates, right? And presumably there might be some, I don't know if this would be drawable very much, but, right? Presumably there would be some wire that's, connected to the top one and a wire that's connected to the bottom one, and it's in an electrical circuit. But there's just two conductors that have opposite charges that are separated by some distance d here, and therefore you get an electric field in exactly the same way we've described before. You have a positively charged thing up here, that's your positive plate, and you have a negatively charged plate down here, that's your plate B. And so therefore you get an electric field from positive down to negative. Same exact stuff we've been talking about. I bet you were expecting a capacitor to turn into some very complex thing, but at its most simple form, that's all it is. So that's called a parallel plate capacitor. And of course, these plates in real life don't extend out to infinity, and so you do get some fringing here at the ends, but whatever. And also, there's fields, that come out here and wrap all the way around here and go from positive to negative in that way as well, since they're not extending to infinity, and there's field line somewhere that goes straight out that way and comes straight in this way, right? All right, so the situation between these plates is one that we literally just talked about, oppositely charged parallel plates, and therefore we already know that the potential difference between the plates is given in the same way that we had described before, right? So this VAB that I labeled is just equal to E times the distance between them is D, right? Before we had E times Y, but this one we're calling the distance between them D, and that is what matters here. So yeah, before we had the negative plate being zero potential, and then up all the way at the top positive plate would be some distance Y away from zero potential. Same deal, you can think of it the same way here, just distance D. So the electric field for these two oppositely charged plates, or at least the uniform charge distribution over a surface, right, can be found using Gauss's law. So he comes back into play. So the electric field, E, which we just declared was a thing before but didn't talk about what it actually might be, via Gauss's law, we know that it's the surface charge divided by this quantity. Let me do a better one. Epsilon naught. So what is this? This is sigma, and it describes a charge per area. It's the surface charge density, right? So density is like how much mass stuffed into how much volume, right? So if you have some brick of some material, it has some mass and it has some volume, so mass per volume is equal to density. Remember that? Well, this is a surface charge density, so it's a similar concept of how much something stuffed into how much something, but in this case we're talking about how much charge is stuffed into how much area, right? So sigma, surface charge density, would be equal to Q, if that's our total charge per plate, per area, and then we have this epsilon naught there, the permittivity of free space. So to be explicit, sigma is equal to surface charge density, and it's also equal to Q, whatever the total charge is, divided by A, whatever the area is of the thing. There's also volume charge density, but here we're just talking about surface charge density. So notice, if we double the magnitude of charge on each plate, so instead of positive Q on the red one and negative Q on the blue one, it's positive 2Q on the red one and negative 2Q on the negative one, then according to these equations we've written down, the magnitude on the charge doubles, the surface charge density doubles, right? So then you'd have 2, right? I'll keep this one just general on its own. You have 2, right? And that doubles, and so that doubles, and so then over here, this doubles, and so that doubles, right? And so the potential doubles. But if we were to take the ratio of charge to the potential difference, so that would be the ratio of charge, which is Q, which we've now doubled, per potential difference, which has doubled as a result, those twos cancel, and it stays the same as the original before we doubled it, right? So that ratio stays constant. And what that ratio is actually called is the capacitance of a capacitor. Capacitance. And we designate that with an italics C, which is going to be hard to draw here. I don't know. Italics C. I'm just going to say italics. Better in a textbook. Coulombs is a capital C, right? Not in italics. Usually from context it's clear if you're talking about a capacitor or capacitance instead of coulomb. I mean, one is just a symbol for a quantity and the other is a symbol for a unit, so there's one difference there. But be careful not to confuse them. And so capacitance, C, which is italics, I don't really know how to do that. Maybe that is equal to Q divided by VAB. So the capacitance of a capacitor is equal to the total charge, right, divided by the potential difference. And that's true of any capacitor, not just parallel plate capacitors. And there's associated units for capacitance, known as the farad, after Michael Faraday. I think there's an electric car company at some point in the past few years called the Faraday. Now you know. And that's given by a capital F, and 1 farad is equal to 1 coulomb per volt. All right. So the more capacitance, C, of a capacitor means the more charge, Q, on its conductors for a given potential difference, VAB, or for a given voltage, V, which means more stored energy. So the more capacitance of a capacitor, the more its ability to store energy, or the ability to store more energy. We will expand upon this in coming lectures on electrical circuits, but for now, I'm going to end with just a little further connection here. So the capacitance of our parallel plate capacitor specifically, if we're talking about in a vacuum, right? So vacuum is something of a insulator because it's not a conductor. So if there's not even air between these two plates, there's just a vacuum, then the capacitance of our, that's not bad, of our parallel plate capacitor, I guess I can do this, doop, doop, it would be equal to, of course, Q over VAB, but what are those things? That's equal to E epsilon naught A over E D, which is equal to epsilon naught A over D. All right, so that, I suppose, might be worth boxing in, because parallel plate capacitors, pretty common test beds for learning this stuff anyway. And the potential energy stored in a capacitor of any kind, right, any kind, is equal to the work required to charge it. This makes sense, right? The potential, elastic potential energy stored in a spring is equal to the work required to compress it or stretch it. The gravitational potential energy that is stored in a body is equal to the work required to lift it up to that position, right? This goes back to that concept that we were saying, flipping it on its head, bringing it from zero potential to some higher potential instead of how much energy you get out of something, letting it drop. So this can be recovered in the form of work done by electrical forces, right? The potential, electric potential energy stored in a capacitor. It can be useful in circuits, right? So it's a store of electric potential energy that, obviously we can make some good use of, and we're going to explore that in following lectures. But for now, the value of stored potential energy can be found, and this is where I have to do some, ellipses, because it requires calculus to show this, and we're not going to go into that. But it can be shown that the electric potential energy stored in a capacitor is equal to Q squared over 2C, equivalently equal to 1/2 CV squared. You like the look of that one? Or equivalently expressed as 1/2 QV. All right, all these free forms are equivalent. They're all valid, might be useful depending on what quantities you may be given in a particular problem, right? It's typically how it goes. But I want to draw your attention to this one, because look how similar this looks to previous things we've seen, right? Pattern recognition. You never expected it to be such a big part of physics. All right, so this is so similar to the form of elastic potential energy of a spring. It's also pretty similar looking to kinetic energy, right? 1/2 mv squared. But it's better analogous. A better analogy is elastic potential energy. So, elastic written all the way out. Potential energy is 1/2 kx squared, this being the spring constant and this being the amount that the spring was stretched or compressed, right? So if this is its natural position, if you then compressed the thing to there, and you had, this is x equals, let's see, this here, x equals 0 because that is its natural resting position, and this here is x equals wherever it is now, or just x, I guess, then delta x, right, is the distance here. That's the amount that it was compressed, and so that is what x refers to. And k is the spring constant. So very, very analogous. So you can kind of think of the capacitance, C, being analogous to the spring constant, K, and the potential difference, V, being analogous to the displacement of the spring, X. So you squeeze a spring, stored elastic potential energy in the spring. You can get that out to do work on some body, right? Give it kinetic energy or something else. You charge a capacitor, you've stored electric potential energy. And I'll leave it at that note. Next lecture, we'll talk about circuits and how we may use this type of electric potential energy to do awesome things like lighting light bulbs and making our world easier. Alrighty.